In this video, I will teach you how, from the definition of sine of an angle, we might deduce the graph of the sine function. Let's begin with a right triangle and call x one of the two angles that is not pi over 2. The sine of the angle x is typically defined as a geometric ratio between the length of the opposite side of x and the length of the hypotenuse. Then, referring to the figure I made, AB over OA. On the other hand, the cosine of the angle x is introduced as the quotient between the length of the cathethus near to x and the length of the hypotenuse, that is, OB over OA. In order to make the simplest possible speech, we can refer to a triangle similar to OAB. Thus, it must have equal angles. In particular, it will have one right angle and one angle equal to x, with hypotenuse of unitary length. In some sense, we are normalizing our figure. We call such triangle OA prime B prime, and OA prime is equal to 1. You can see the two similar triangles in the figure. OA prime B prime is yellow and OAB is blue. The yellow triangle is the normalized version of the blue triangle, the initial one. Now let's continue considering the fact that these two triangles are similar. This fact implies that the measure of the corresponding sides show a constant proportion. Their sides are proportionate. In particular, the hypotenuse of the yellow triangle divided by the hypotenuse of the blue triangle provides the same value that we obtain dividing the cathethus of the yellow triangle by the corresponding cathethus of the blue triangle. The proportion can be written using a column as OA prime to OA equal A prime B prime to AB. The very identical formula can be done considering the other side of the triangle. Indeed, we can write OA prime, hypotenuse of the yellow triangle, to OA, hypotenuse of the blue triangle, equals OB prime as the cathethus close to x in the yellow triangle to OB, the cathethus close to x in the blue triangle. Saying that two triangles are similar actually has exactly this, meaning that their sides have the same proportions. From the two equalities just written, we deduce AB over OA equals A prime B prime over OA prime. And since OA prime equals 1, we obtain that the sine of x coincide with the side A prime B prime in the normalized triangle. Henceforth, in the right triangle with hypotenuse 1 and angle x, the sine of x can be identified as the length of the side opposite to the angle x. On the other hand, from the other ratio, we deduce that OB over OA equals OB prime over OA prime, and since OA prime is equal to 1, OB over OA, the cosine of x, equals OB prime. And consequently, in the right triangle of hypotenuse 1, the cosine of x is identified with the length of the cathethus close to the angle x. Now look at the figure. According to how wide is the angle x in the right triangle with hypotenuse 1, we will obtain different values of the sine and cosine associated to that angle, At this point, it would be exactly very nice to be able to deduce the shape and the pattern of that dependence, of the values of the sine x and cosine x according to the width of the angle x. In order to be as precise as possible, I ask MATLAB to help me in the representation of the circumference of radius 1 centered at the origin in the Cartesian plane. Now consider a moving point on that circumference, and let me call x the arch, the path of the point from the initial position. X describes the position of the point on the circumference, and measured in radians, it gives exactly the angle made by the black rotating segment with the positive part of the horizontal axis. We recognize the cosine of x as the oriented projection of the position on the horizontal axis. Oriented projection means exactly that we will consider also the sine of the projection in a way that I'll describe in a moment. Similarly, the sine of x can be seen as the result of the oriented projection of the position x on the vertical axis. Thus, when x is 0, the cosine is equal to 1 and the sine is 0. As far as x is in the first quadrant, both sine and cosine are positive. Else, if x is in the second quadrant, the sine is positive and the cosine is negative, and so on. In the third quadrant, both projections, sine and cosine, will be negative, and in the fourth quadrant, the cosine is back to be positive and the sine remains negative. The point can keep on moving on that circumference. It can rotate around the origin, and at each rotation, sine and cosine will attain the very same values. The sine function represents the sides of the sine with respect to the position x on the circumference that is now represented on the horizontal axis. That function starts from the origin and is increasing until it reaches its maximum value, that is 1, attained when x is the right angle pi over 2. For the values of x between pi over 2 and pi, the sine remains positive but progressively decreases to the value 0 when x is the flat angle. The sine function keeps on decreasing, assuming now negative values, and reaching its minimum value, negative 1, when x is equal to 3 over 2 pi. After this position, the sine function becomes increasing again, and it turns to reach the value 0 again for x equal to pi. So then, we have found the first oscillation, so to speak, the essential pattern of the sine function. It's a kind of way. As x rotates around the origin on the trigonometric circumference, making another lap, the graph of the sine function is replicated identical. Rotation after rotation, that is, adding 2 pi to x, we obtain the characteristic periodic shape of the sine function.